federated learning is a technique that allows multiple clients to collaboratively train a neural network without sharing their data by outsourcing the training to the individual clients. However, the drawback of this is that the server that orchestrates this process can no longer control the training, such that an attacker which compromised some of the clients could actually try to inject a backdoor into the system. Together with my colleagues from the System Security Lab of TU Darmstadt, we designed therefore DeepSight to mitigate such poisoning attacks. But let's just first go a step backward and make a small recap how federated learning works. I will keep it short as we have just saw an overview, but just for the people who just joined. Here we have in federated learning, we have multiple clients which are connected to a central server, and each client has a private data set that doesn't want to share. In centralized learning, plain federated learning, the clients would need to send their data sets to a central server. But if you consider applications with very sensitive data, this is not an option. Therefore, in federated learning, the clients just train their data as an own neural network locally on their private data set, and after the training is finished, they just send the trained parameters to the server, which aggregates these individual models, for example, by averaging them, and then distributes this model back for the next training rounds. This has many advantages. First of all, it improves the user privacy as the data never leaves the respective client. Second, it improves the computation efficiency as the training is parallelized and outsourced. And finally, also the performance of the resulting model is improved as now more data can be utilized. So far about the nice things of federated learning. Let's now look on the drawbacks. There's one major problem, namely that an attacker who has compromised some of these clients can actually manipulate the training data set to inject a backdoor into the local model when it's trained on this data set. When this a poisoned model is now sent to the server, not just the aggregated model will become poisoned, but after distributing back, the model of every single client will contain this backdoor. How could such a backdoor look like? For example, in case of image recognition, for example, in the context of self-autonomous driving cars, such a backdoor could manipulate the component that recognizes the traffic signs to recognize all traffic signs indicating 30 kilometers per hour as 80 kilometers per hour. To be honest, I don't want to sit in such a car. For me, it's too dangerous. Second, another application is, for example, in an NLP application that suggests words on smartphones. Here, an adversary could try to inject advertisement such that certain brand names are always suggested if a certain problem is mentioned. And another application where a backdoor could be not desired is IoT network intrusion detection system, which inspects the network traffic of IoT devices to check whether they are infected by malware. Here, a backdoor could create a blind spot for a certain malware. Obviously, none of these backdoors is actually desired, so there are a number of approaches which already try to mitigate these backdoor attacks. These can be categorized mainly into two classes. First, approaches that try to prevent that the poison models are actually used in the aggregation, and secondly, approaches that accept that some poison models might be included into the aggregation, but they try to restrict the impact of the poison models. For the first category, there are a number of approaches use clustering. So, for example, here two approaches use HDB scan, or our uses k-means. Other approaches try to select parameters that are for sure benign. So, for example, by calculating the parameterized median for the aggregation, or there is another approach that the previous speaker already mentioned, CRUM, for example, selects a model as aggregate model that minimizes the distances to the other models and assumes that the majority of clients is benign. However, the drawback of these approaches that all target on detecting outliers is that the models even the benign models can actually look different. There can also be outliers inside. If we, for example, consider the NLP application, then different users might behave differently and type different texts. So also the resulting models which are trained on these different data will look different, such that we also will have their outliers. And if we now exclude benign outlier models here, then the resulting model will never be trained on the data of these clients, such that it will not perform well on these data. From the second category, we just learned in the previous talks that also weak differential privacy can be applied to mitigate these backdoor attacks. Unfortunately, in our experiments, we observed that it can be circumvented by ensuring that the backdoor is strongly trained into the model. So, for example, by using a higher amount of training samples for the backdoor behavior during the training. And by this, this defense can be circumvented. Another approach here, fool's gold, just assumes that the data of different benign clients are very different, while the data of the different malicious clients is very similar as they try to inject the same backdoor. However, this can be easily circumvented by just making the poison models different to each other. To address these shortcomings, we designed DeepSight. But let's first have a look on a few observations that we made to motivate the approach. The first observation that is important here is that the training data for the benign main task is way more complex than for a backdoor. For example, if you consider a natural language processing application for suggesting words, then the benign clients need to train the model to a whole language consisting of many different words, many grammar rules, and way more. While a simple backdoor to inject advertisement just could consist of a single sentence, 5 words, and always the same order. So this backdoor training data are way less complex than the benign training data here. The second observation that we made is that the backdoor attack is most effective if the adversary strongly trains the backdoor into his poison models. If you consider a poison model that is just weakly trained by using few samples for the backdoor, such that the predictions are barely changed from the benign prediction towards the backdoor target, and then you combine this with many benign models during the aggregation, then the impact of the backdoor will become negligible. Of course, the adversary can actually try to compensate this by upscaling the model updates to boost the attack impact during the averaging. However, here clipping, which is part of differential privacy, has been shown to be quite effective against these. So, how can we now use these observations? If we have here we have multiple clients which train their local models, and 4 of them are benign, 2 are malicious, and after the training we want to know which of these are benign, which are malicious. The best option, of course, would be here to just inspect the training data. But unfortunately, that's not possible because the client won't allow this to us, as this would violate their privacy. So we need to take the second best option. We need to look on the models which were trained on these data sets and check whether the models contain certain artifacts that are typical for poisoning. For this, we developed 2 techniques. The first one is the normalized update energies. This, or short NUPs. This technique looks on the parameter updates for the output layer and looks there for discrepancies. In the output layer for a neural network, usually each neuron represents one category that the neural network can actually recognize. So here in this example, we have 3 output layer neurons. So this network could, for example, distinguish 3 different categories. So for example, in case of image classification, it could distinguish whether an image contains a car, a dog, or a ship. And this NUP technique here then looks on how these updates are distributed to the individual neurons. So it checks what is the magnitude of the overall update for the total layer, and then looks on how these are distributed to the individual neurons. So in this example here, the first neuron received 9% of all updates, the second 76%, and the last one 17%. During training a neural network, for every sample, all parameters of the network are adapted very slightly. So if a label occurs way more often than the other labels, then also the respective output layer neuron will be changed more strongly, such that this NUP distribution can be actually used to very roughly estimate the distribution of labels in the training data. And by this, we get a fingerprint of the training data. As we've seen on the previous slide, for backdoor data, they usually focus on way fewer labels than the benign data. Therefore, they are more focused. Since the NUPs make a rough estimation of the training data labels, we can also use this to identify suspicious models, because then also the NUPs are focused on few unique neurons. in this example here, for example, one neuron received 76% of all the updates. If we now assume that the majority of models, the NUPs are well distributed among all neurons, so for example, all other models received each 1/3 of the updates, then this 76% here is very suspicious. If you want to have a closer look on all these techniques and check how they are calculated and how we identify this focus, then please have a closer look on the paper to check out these equations and all their meanings. Don't read them now. So the second technique that we introduced to analyze the models look on the predictions of the neural network. Usually a neural network, when taking an input sample, predicts for every output category probability that this specific sample belongs to this category. But when we train now a neural network on the local data, then these predictions will obviously change. And the second technique looks on exactly these changes. It compares these changes to the predictions of the original model by dividing them, and that's why it is called division differences. By dividing these predictions, we obtain a second fingerprint that we can use later for identifying Poisson models. The main advantage about compared to the NUPs is here that these predictions consider all layers, while the NUPs just looked on the final layer. The division differences considered all layers, so that we just get a second perspective on the models, and we can use this later. A problem in this context is unfortunately that for doing predictions, we actually need to have something to predict on. We need input data. It's not really realistic to assume that the server has these data as the client won't share these data. Luckily, we can, here we are only interested in the difference in the predictions. So we are not interested in the actual predictions, but just in the differences. So because of this, we can use at this place here random data that the server can easily generate. And again, if you want to have a closer look on these techniques, please check it out in the paper. Let's now look on how this technique can be used to identify Poisson models. DeepSight takes the model updates that it received by the clients and then uses these techniques to apply a filtering. I will explain this filtering in more detail on the next slide, but for now, let's continue with the filtered models, which are then forwarded to the clipping component, which downscales the model updates if their magnitude, if their distance to the original model is too high, to prevent that the adversary uses only weakly trained models and upscales them to boost their impact. Finally, these filtered and clipped models are then aggregated and sent back to the clients. Let's now look on how this filtering works in detail. Here again, we have multiple clients, 4 benign clients and 2 malicious clients. One of these malicious clients actually trains its model strongly for the backdoor, for example, by using a high amount of training samples for the backdoor, while the other one uses only a weakly trained model, here indicated by this bright red color. After this training is finished, these models are sent to the server, which then extracts these fingerprints. So for each model, we extract the NOIPs, the DDIFs, and as a third fingerprinting technique, we also calculate the pairwise cosine distances to all the other models. These fingerprints will be mainly used in the second next step, the clustering. The classification that comes now uses mostly the NOIPs and analyzes them and to check whether there are models where the NOIPs are significantly more focused on few neurons compared to the majority of models. If this is the case, then we label this model as suspicious, and otherwise we label it as inconspicuous. As you can see here, the benign models were in this toy example modeled correctly, and the Poisson model that was trained strongly was also recognized correctly as suspicious. But unfortunately, here in this example, we didn't recognize the weakly trained model, as this is a false negative. To fix this, we apply the second step, the clustering, which uses all 3 fingerprints that we just extracted. We apply clustering on them to cluster the models according to their training data distributions and assume that models with similar data should also be labeled similar. Here we have now a clustering, but we don't know which of these clusters are now benign, which are malicious. To fix this, we combine it with the classification, and then we simply count for each cluster how many models in this cluster were labeled as benign, how many as suspicious, And if more than 1/3 of the models is labeled as suspicious, then we just exclude all models in this cluster. And by this, we can fix the false negative and can continue only with the benign models. Let's now, as a last step, have a short look on the evaluation results for DeepSight. Here we compared against the baseline that just uses federated averaging without any further defense, and we use 4 metrics in total for the comparison. First, we calculate the accuracy on a test data set consisting of test samples for the backdoor behavior, and analogously for a benign data set consisting of samples for the benign main task. And thirdly, to evaluate the ability to distinguish benign and poison models, we also measure the precision and recall. We use in total 3 data sets here. First, MNIST, which consists of handwritten images of handwritten digits, and is a standard benchmark data set for federated learning. Here, the attack is very successful. The backdoor accuracy is 96.3%, while the main task accuracy is unfortunately dropped by this attack from around 96% to 58.9%. In comparison, DeepSight here is able to distinguish benign and poison models. Precision and recall in both cases are both 100%. The classifier here didn't perfectly recognize all poison models correctly, but this was compensated by the clustering step. The next application uses the Reddit dataset that we have just seen in the previous presentation. Here again, the backdoor accuracy is 100%, while the main task accuracy is 22.4%. NLP is unfortunately a little bit more complex than recognizing handwritten images, so even without attack, the main task accuracy is only 22.6%. Again, DeepSight here is able to distinguish benign and poison models, such that the backdoor accuracy is 0 and the main task accuracy remains at 22.6%. Finally, the last application is the IoT network intrusion detection system that I already mentioned in the beginning. Here, again, backdoor and main task accuracy are both 100% in case of the attack, while by using DeepSight, this is reduced to 0%, main task accuracy remains, and it is able to distinguish these models. Of course, this was just a very small excerpt of all the experiments that we have performed, so if you want to have a closer look on the evaluation, please check it out in the paper. Thank you. Any questions?